Perceptual illusions are not mere parlor tricks, but profound revelations about how the brain actively constructs your reality. What you see is rarely a carbon copy of the world, but rather a sophisticated prediction. Your brain sits in total silence and absolute darkness inside the vault of your skull, never touching the light directly. If you find comfort in uncovering these quiet truths, feel free to subscribe as we unravel the mysteries of the mind. The only contact your brain has with the outside universe comes through electrochemical signals traveling along sensory cables. It receives streams of coded data, not pictures, yet it generates the rich, colorful panorama you believe is happening right now. This creates a startling truth often cited by neuroscientists. Reality is essentially a controlled hallucination. When your internal simulation agrees with the external data, we call it perception. But when there is a mismatch, the result is an illusion. These errors are not failures of the system, but features of a high-speed prediction engine designed for survival rather than accuracy. The brain prioritizes speed over precision because noticing a threat in the shadows is more important than knowing the shadow's exact texture. This prioritization leads to another fascinating biological fact regarding time. Because it takes physical time for neural signals to travel from the retina to the visual cortex, you are technically living in the past. Current estimates suggest there is a lag of approximately 80 to 100 milliseconds between an event occurring and your conscious perception of it. To compensate for this delay, the brain anticipates the future position of moving objects, effectively showing you where things should be rather than where they physically are at this exact nanosecond. The machinery required to maintain this continuous simulation is immense. While hearing or touch occupies smaller territories of the cortex, vision dominates the brain's geography. Roughly 30 to 50% of the cerebral cortex is dedicated to visual processing, involving billions of neurons firing in synchronization. This is why closing your eyes can feel so restful, as you are instantly shutting down the primary workload of your neural processor. The energy consumption of the brain remains high even at rest, burning about 20% of your body's metabolic energy despite weighing only 3 pounds. Much of this energy goes towards filtering out information. Your senses are bombarded with 11 million bits of information every second, yet the conscious mind can only process about 50 bits. This extreme filtering means that what you perceive is less about what is there and more about what your brain decides is worth noticing. The gap between raw data and conscious awareness is where the secrets of perception reside. To bridge that gap, we must first look at the biological hardware that captures the light. The human eye is often compared to a camera, yet it operates with a series of distinct physical limitations that the brain must constantly work to hide. For instance, the physics of the biological lens dictate that light entering your pupil projects an image onto the retina that is technically upside down and reversed left to right. Your brain, in its quiet efficiency, flips this world right side up instantly that you never even suspect the inversion occurred, correcting the orientation of reality before it ever reaches your conscious awareness. Even more curious is the architecture of the retina itself. There is a specific point at the back of the eye known as the optic disc, where the optic nerve creates a tunnel to exit the eyeball and travel to the brain. Because this thick bundle of nerve fibers occupies this space, there is no room for light-sensitive cells. This creates a physiological blind spot in every single person's field of view, a region where you are technically blind. If you were to close one eye and focus on a specific point, there is a distinct area off to the side where objects simply vanish. Yet you do not see a gaping black hole in your vision. The brain simply patches the void. It samples the patterns, textures, and colors surrounding the blind spot and essentially copy-pastes them to fill the gap, hallucinating a seamless reality to ensure your visual field feels complete. The limitations continue with the sensors themselves, the rods and cones. Their distribution represents a stark evolutionary trade-off between sensitivity and clarity. Cones, which detect color and fine detail, are tightly packed only in the very center of your vision, a tiny pit called the fovea. This is the only part of your eye capable of high-definition focus. Rods, on the other hand, dominate the vast outer regions of the retina. They are incredibly sensitive to motion and dim light, a trait inherited from ancestors who needed to spot predators in the dark, but they are almost completely blind to color and unable to resolve fine detail. This leads to a startling truth about your current perception. Because the periphery is largely colorblind and low resolution, the rich, colorful panorama you believe you see is a mental fabrication. Your eyes make rapid, jerky movements called saccades to snap clear details, and the brain stitches these snapshots together, painting color into the gray periphery based on memory and expectation.
You feel as though you are viewing a continuous, high-definition scene, but you are actually looking through a narrow keyhole clarity while your mind invents the rest of the picture. This reliance on internal construction over external input becomes even more apparent when we examine how the brain decides to assign color to these signals. This subjective assignment of reality is perhaps nowhere more obvious and nowhere more hotly debated than in the phenomenon of color constancy. You might recall a certain photograph that broke the internet in early 2015, a simple, low-quality image of a lace-trimmed cocktail dress. To roughly half the population, the garment was clearly black and royal blue. To the other half, looking at the exact same digital file on the exact same screens, it was undeniably white and gold. This was not a mass hallucination, nor was it a prank, but rather the most famous accidental experiment in the history of visual neuroscience. It revealed a fundamental mechanism called color constancy, which is your brain's tireless effort to ensure that an object looks the same regardless of the lighting conditions. In the real world, the light bouncing off an object is a mix of the object's reflectance and the color of the light source. A red apple in blue daylight reflects different wavelengths than a red apple under a yellow candle. Yet you never look at the apple and think it has changed color. Your brain automatically and instantly subtracts the estimated color of the light source to reveal what it believes is the true color of the object. With the dress, the photograph was taken in a lighting that was perfectly ambiguous. It lacked the necessary context clues, known as anchors, to tell your brain if the dress was in a deep blue shadow or under a bright, washing out yellow light. Because your visual cortex had to make a guess, it relied on your prior experiences and internal models. Neuroscientists hypothesize that this split in perception may even correlate with a person's sleep-wake cycle. If you are a lark who spends most of your waking hours in natural daylight, your brain might be primed to interpret ambiguous lighting as a bluish shadow. Consequently, your brain subtracts the blue information from the image, leaving you with a perception of white and gold. If you are a night owl accustomed to artificial yellow light, your brain might assume the dress is being washed out by warm bulbs. It subtracts the yellow, leaving the deep blue and black tones. The image itself sat on a perceptual knife edge, proving that color is not an inherent property of the object you are holding, but an interpretation created inside your skull. This corrective mechanism is usually helpful, but it can be easily tricked by carefully crafted images, such as the famous illusion of the gray strawberries created by psychology professor Akiyoshi Kitaoka. In this picture, you see a tart topped with a pile of strawberries that appear clearly, vibrantly red. However, if you were to isolate the pixels of the fruit using a color picker tool, masking the surrounding context, you would find not a single pixel of red in the entire image. The pixels are actually purely gray and cyan. The image is overlaid with a cyan or blue-green filter. Because your brain recognizes the objects as strawberries, items you know from lifelong memory to be red, and simultaneously detects the bluish cast of the lighting, it overcompensates. It subtracts the cyan overlay from the gray pixels. In the neurological mathematics of color perception, gray minus cyan equals red. Your brain effectively hallucinates the red color to make sense of the scene, prioritizing its understanding of how the world should look over the raw data hitting the retina. It demonstrates that you do not see the world as it is, you see the world as it is useful to see it, with your mind constantly adjusting the dials to maintain a consistent narrative. This process of adjustment begins earlier than you might expect, largely driven by your visual system's intense obsession with contrast. To your brain, the absolute brightness of an object is far less important than where that object ends and another begins. This biological prioritization is beautifully illustrated by the Hermann grid, a classic pattern consisting of a simple black background overlaid with a grid of white horizontal and vertical lines. When you gaze at this image, you will almost certainly perceive ghostly, flickering gray dots appearing at the intersections where the white lines cross. These phantom dots are elusive. They vanish the moment you try to look directly at them, only to reappear instantly in your peripheral vision, taunting your attempt to pin them down with direct focus. This phenomenon is not a mistake or a failure of the senses, but a distinct feature of how your retinal ganglion cells operate through a mechanism known as lateral inhibition. To understand this, we must look at the microscopic architecture of the retina. The neurons here are organized in such a way that an excited cell tends to reduce the activity of its immediate neighbors. It's a form of friendly neural competition where cells effectively shout over one another to ensure the sharpest possible signal is sent to the brain. This creates a system of edge enhancement, ensuring that boundaries between light and dark are crisp and unmistakable. Consider a retinal cell responsible for observing a section of the white grid line between two black squares.
This cell receives strong stimulation from the white light in its center, while its neighbors, which are looking at the black squares, remain relatively quiet. Because the neighbors are quiet, they do not inhibit the center cell, allowing it to fire a strong, clear signal that the brain interprets as bright white. However, the situation changes dramatically at the intersection. A cell positioned right at the crossing point of the white lines is surrounded by white on all four sides. While it receives strong stimulation from its center, it is also bombarded by inhibitory signals from its highly active neighbors on the top, bottom, left, and right. These active neighbors dampen the center cell's response, effectively muting its output. Consequently, the brain interprets this weakened signal not as pure white, but as a slightly dimmer gray. This explains the ghostly dots, but it also explains why they disappear when you stare directly at them. The center of your vision, the fovea, contains a much denser packing of cells with much smaller receptive fields. In this high-resolution zone, the area of inhibition is too small to span the entire intersection, allowing the brain to perceive the white space accurately without the interference of neighboring suppression. This elegant machinery reveals that your eyes are not passive cameras, but active editors, sharpening the boundaries of the world before the image ever reaches your conscious mind. This active editing process becomes even more fascinating when we leave the mechanics of the retina and enter the complex interpretive centers of the cortex, where one of the most famous demonstrations of visual logic resides. In 1995, vision scientist Edward Adelson published an image that has likely caused more disbelief and cognitive friction than any other optical puzzle in history. It depicts a simple three-dimensional checkerboard pattern with a green cylinder resting on top, casting a soft diagonal shadow across the board. We see a standard pattern of alternating light and dark squares, much like a chessboard. Within this scene, there is a dark square outside the shadow, labeled A, and a light square deeply immersed within the shadow, labeled B. To every human observer, square A looks charcoal black, while square B appears to be a muted white or light gray. The visual distinction feels stark, obvious, and undeniable. However, if you were to take a digital color dropper or a physical piece of gray paper and isolate those two specific squares, you would find something deeply unsettling. Square A and square B are exactly the same shade of gray. They reflect the precise same amount of light into your eye, pixel for pixel. Even when you were told this fact, and even if you verify it by covering the rest of the image, the moment the full context returns, the illusion reasserts itself with full force. You cannot unsee the brightness difference. This stubbornness reveals that your visual system is not designed to be a physical light meter. It is not interested in the raw number of photons hitting your retina. Instead, it is obsessed with determining the true nature of surfaces in a three-dimensional world, a task that requires sophisticated guesswork. The brain constantly faces a challenge known as the inverse optics problem. It receives a flat two-dimensional image on the retina and must reconstruct the three-dimensional reality that caused it. When the brain analyzes Adelson's checkerboard, it identifies the cylinder and the resulting shadow. It understands the physics of light, specifically that shadows make surfaces appear darker than they truly are. Crucially, it analyzes the nature of the boundaries. The shadow has a soft, fuzzy gradient known as a penumbra, while the painted squares have sharp, hard edges. The brain uses these clues to categorize the darkness. It decides that the darkness covering square B is merely a result of the shadow, not a change in the paint on the board. To determine the true color of the square, the brain subconsciously adds luminance back into the equation, compensating for the shadow's dimming effect. It effectively tells your conscious mind that although this square is sending gray light to the eye, it is sitting in a shadow, so it must actually be white. This calculation happens instantly and involuntarily. If your brain simply reported the raw luminance values, you would perceive a confusing patchwork of grays rather than a coherent object. By prioritizing a stable interpretation of the physical world over the literal accuracy of the light entering your eye, the brain ensures you can recognize objects correctly regardless of whether you are standing in bright sunlight or a dim room. It is a brilliant evolutionary trade-off where raw accuracy is sacrificed for meaningful utility. This prioritization of meaning over raw data is perhaps most famously illustrated by a simple geometric puzzle known as the Muller-Lyer illusion. It presents two horizontal lines of exactly equal length. One line is capped at both ends by arrowheads pointing inward, while the other is capped by fins pointing outward. To the human eye, the line with the outward-pointing fins appears significantly longer than its counterpart, a distortion that persists even when you measure them with a ruler and prove it to yourself. For decades, psychologists debated why this occurred, eventually settling on a theory that reveals how deeply your environment shapes your biology.
It is called the carpentered world hypothesis. The theory posits that the illusion works because your brain is subconsciously interpreting the lines as corners in a three-dimensional space. The line with the outward fins resembles the inside corner of a room, where the walls recede away from you. The line with the inward arrowheads resembles the outside corner of a building,
jutting toward you. Because your brain assumes the inside corner is further away, it applies a rule of size constancy. The logic holds that if two objects cast the same size image on the retina, but one is determined to be further away, the distant object must be physically larger. You do not consciously think about corners or walls, but your visual cortex runs this calculation instantly. This explanation was bolstered by fascinating cross-cultural studies conducted in the mid-20th century. Researchers found that people living in environments without straight lines and right angles, such as the Zulu people in South Africa, whose traditional architecture consisted of round huts and curved boundaries, were largely immune to the illusion. They saw the lines as they actually were, simply because their brains had not been trained to interpret every angle as a rigid architectural feature. This reliance on depth cues becomes even more powerful when we introduce linear perspective, as demonstrated by the Italian psychologist Mario Ponzo in 1911. The Ponzo illusion typically displays two converging lines, looking much like railroad tracks receding into the distance. Two horizontal bars of identical width are placed across these tracks, one near the bottom and one near the top. Despite being physically identical, the upper bar appears much wider to the observer. The mechanism here is similar to the arrow illusion, but relies on your brain's understanding of the horizon. The converging lines tell your brain that the top of the image is far away. Since the upper bar spans the distant tracks, your brain concludes it must be a massive object to span such a width at that simulated distance. It essentially magnifies your perception of the object to match the logic of the scene. It is a remarkable demonstration that you do not see the world exactly as it appears on the back of your eye. You see a construction, a best-guess model built from years of navigating a world full of roads, hallways, and horizons. This internal construction of reality extends far beyond the walls of a distorted room and reaches all the way to the cosmos itself. Perhaps the most famous and persistent glitch in our visual software is the moon illusion, a puzzle that has fascinated astronomers, artists, and philosophers for thousands of years. You have likely stood under the open sky on a warm evening and watched a full moon rising above the distant tree line. At that moment, hovering just above the horizon, the moon appears colossal, a giant glowing orb that seems to dwarf the landscape and hang heavy in the air. Yet hours later, when that very same moon has climbed high into the darkness of the zenith, it looks tiny, lonely, and insignificant. For centuries, curious observers, including Aristotle, believed this was a physical phenomenon. They theorized that the Earth's atmosphere acted like a magnifying lens, swelling the image of the moon when we look through the thicker, mistier air at the horizon. It's a beautiful, intuitive explanation that feels true because the horizon often looks hazy and atmospheric. However, it is entirely wrong. If you were to take a camera and photograph the moon at the horizon and again at its peak, the resulting images on the film would measure exactly the same width. In fact, if you turn your back to the horizon, bend over, and look at the rising moon between your legs, the illusion often vanishes and the moon shrinks back to its normal size. The lens of the eye and the lens of the camera receive the exact same raw data. The magnification is not happening in the air, it is happening entirely inside your mind. This brings us back to how your brain handles depth in the vast theater of the outdoors. The leading scientific explanation for this celestial trick is known as the apparent distance hypothesis, which relies on the shape of the sky itself, or rather, the shape your brain assumes the sky to be. We tend to perceive the sky not as a perfect hemisphere, but as a flattened dome, almost like an upturned soup bowl that has been pressed down at the top. Because we have ample visual cues on the ground, trees, buildings, hills, and roads shrinking into the distance, our depth perception tells us that the horizon is incredibly far away. It feels distant.
However, when we look straight up, there are no depth cues. There are no train tracks converging, no textures to judge, and no objects to compare against. Consequently, the brain perceives the zenith of the sky as being much closer to us than the horizon. Here is where the illusion takes hold. Your retina receives an image of the moon that is constant in size, roughly half a degree wide, regardless of where it sits in the sky. But your brain is running a silent calculation based on that flattened dome model. It thinks the object at the horizon is extremely far away, yet it is producing the same size image on the eye as the object overhead, which is close. To make sense of this discrepancy, the brain subconsciously decides that for the horizon moon to be that far away and still look that big, it must be physically massive. It scales up your perception of the moon's size to account for the perceived distance. It is essentially the same mechanism behind the Ponzo illusion, where two identical lines drawn on a converging railroad track appear to be different lengths because the brain is compensating for perspective. This effect is compounded by context. At the horizon, the moon sits alongside terrestrial objects that provide scale, houses, mountains, or skylines. High in the sky, it floats in an empty void of black, offering no comparative reference. This relates closely to the Ebbinghaus illusion, where a central circle surrounded by smaller circles looks huge, while the same central circle surrounded by large circles looks small. The vast emptiness of the upper atmosphere makes the moon seem diminished, while the clutter of the horizon makes it seem grand. It serves as a nightly reminder that size is not an absolute truth, but a relationship defined by where an object sits in the story your brain is telling. So when you gaze up at the night sky, you are not acting as a passive camera recording the universe. You are an active participant, bending the cosmos to fit the internal architecture of your mind. This internal architecture is nowhere more evident than in a famous distortion known as the Ames room, a space designed specifically to exploit your brain's rigidity. At a glance, peering through a small peephole into this specially constructed environment, you see a perfectly normal rectangular room with a checkered floor and windows on the back wall. It appears entirely mundane, perhaps resembling a spare bedroom or a tidy study. However, this normalcy is a carefully calculated geometric lie. The room is actually shaped like a trapezoid, with the floor built on a steep incline and the walls constructed at sharp, unexpected angles, meaning that one rear corner is significantly farther away from your eye than the other. The illusion is strictly monocular, meaning it works only when you look with one eye, denying your brain the stereoscopic depth perception that usually helps you judge distance. Because your mind is so heavily conditioned to believe that rooms are box-shaped with right angles, it refuses to accept the trapezoidal reality. It creates a rigid assumption that the floor is level and the back wall is perpendicular to the line of sight. When a person stands in the near corner, they fill a large portion of your vertical field of view, appearing like a giant whose head nearly scrapes the ceiling. When they walk across the room to the far corner, they are actually moving significantly further away from you, but because the room disguises this depth, your brain creates a different explanation. Instead of seeing the person walking into the distance, you see them physically shrinking in real time. It is a startling failure of size constancy, where the brain sacrifices the stability of the human form to maintain its belief in the stability of the room's architecture. This demonstrates that your perception of size is not an absolute measurement, but a derivation based on your estimation of distance. If the distance cues are rigged, the size calculation collapses. This specific manipulation of depth cues, known as forced perspective, eventually moved out of the psychology laboratory and became an essential tool in filmmaking.
Before the advent of heavy computer-generated imagery, directors had to rely on practical geometry to sell the impossible. The most famous application of this technique is likely found in the production of The Lord of the Rings. To make the hobbit Frodo appear significantly smaller than the wizard Gandalf, the actors were rarely standing next to each other in the way it appeared on screen. Using a technique that mimicked the principles of the Ames room, the filmmakers positioned the actor playing Gandalf much closer to the lens, while the actor playing Frodo sat further back. Through precise alignment of props, tables, and lighting, the camera compressed the space between them, flattening the depth until the eye could no longer distinguish the distance. What made this cinematic application particularly revolutionary was the use of motion control cameras that allowed the lens to move while shifting the actors and props simultaneously. Usually, if you move your head or the camera, objects at different distances shift relative to one another, a phenomenon called motion parallax that reveals the true depth of the scene. By synchronizing the movement of the camera with the movement of the set, the filmmakers effectively trapped the brain in the illusion, denying it the motion cues it desperately needed to solve the visual puzzle. We trust the geometry of the room more than we trust the logic of our own eyes, allowing spaces to warp our understanding of the things we see within them. This internal reliance on internal prediction over raw visual data bleeds into how we interpret the random textures of the natural world. It leads us to the peculiar sensation of being watched by objects that have no eyes, a phenomenon that highlights just how desperately the human brain seeks to find company in a solitary environment. Take a moment to let your mind drift back to the ceiling patterns of your childhood bedroom, or perhaps a long car ride where you stared at the clouds. Did you ever look at a standard electrical outlet, the grille of an automobile, or a knot in a wooden door, and suddenly feel like it was looking back at you?
If you recall a specific object that seemed to have a personality or a face when you were young, let me know in the comments, because that experience is a fundamental part of being human. This psychological phenomenon is known as pareidolia. It is the tendency to interpret a vague or ambiguous stimulus as something specific and meaningful, and the most common manifestation is seeing faces. This is not a glitch in your visual system, but rather a highly specialized feature running on overdrive. The command center for this operation is a small region in the temporal lobe known as the fusiform face area. This part of the brain is dedicated almost exclusively to facial recognition, and it is aggressive in its duties. Neuroscientists have found that the fusiform face area activates incredibly quickly, processing a potential face in as little as 130 milliseconds. This happens faster than your conscious mind can analyze the object, meaning you feel the presence of a face before you realize you are looking at a toaster or a tree stump. The reason for this hair trigger sensitivity is evolutionary survival. For our ancient ancestors, the ability to instantly recognize a face was a matter of life and death. In the wild, identifying a friend versus a foe or a predator hiding in the tall grass had to happen instantly. Evolutionarily speaking, the brain faces two types of errors. A type 1 error is a false positive, believing there is a tiger in the bushes when it is just a rock. A type 2 error is a false negative, believing there is just a rock when it is actually a tiger. The cost of the first error is a moment of unnecessary fear. The cost of the second error is being eaten. Therefore, nature selected for brains that were paranoid, wiring us to see faces where none exist rather than risk missing one that does. This hardwired survival mechanism explains some of history's most famous visual illusions.
In 1976, NASA's Viking 1 orbiter captured an image of the Cydonia region on Mars, revealing a formation of shadows and light that looked undeniably like a human face staring up from the dusty surface. It captivated the world and sparked decades of speculation about ancient civilizations. It was only later, with higher resolution photography, that the face on Mars was revealed to be a natural mesa shaped by erosion and lit by a low sun. The same neural pathway is responsible for the frequent sightings of religious figures in mundane items, from grilled cheese sandwiches to water stains on a highway underpass. We are social creatures who project agency and emotion onto the void, trusting the geometry of a face even when our logical mind tells us it is just a play of light and shadow. While our brains are desperate to find social meaning in static patterns, they are equally obsessed with tracking the dynamic flow of the physical world. This brings us to one of the most hypnotic and enduring phenomena in the history of perceptual science, widely known as the motion aftereffect. The discovery of this illusion dates back to the Scottish Highlands in 1834. A geologist named Robert Adams was standing before the Falls of Foyers, watching the relentless cascade of water crashing down into the dark pool below. He stared fixedly at the churning white water, entranced by the continuous downward motion, allowing the image to wash over his retina for several seconds. But when he finally shifted his gaze to the damp, mossy rocks beside the waterfall, he witnessed something physically impossible. The solid, stationary cliffs appeared to be surging upwards, rising against gravity in a ghostly motion that directly opposed the direction of the falling water. This sensation, which Adams promptly documented, was not a hallucination in the traditional sense, but a fundamental revelation of how your visual cortex processes change over time. Inside your brain, specifically in the movement processing center, known as V5, you have distinct populations of neurons dedicated to specific directions. Imagine a control panel with different dials for up, down, left, and right. Under normal circumstances, when you look at a still photograph or a sleeping cat, the up neurons and the down neurons are firing at a quiet resting baseline. They cancel each other out perfectly, resulting in the perception of stillness. It is a neural stalemate. However, when you stare at a waterfall, the neurons tuned to downward motion are forced to fire rapidly and continuously. They work at maximum capacity. Over time, these specific cells fall victim to neural adaptation, which is essentially a physiological form of fatigue. They lose their sensitivity. When you suddenly look away at the stationary rocks, those tired down detectors fall silent to recover. Meanwhile, the up detectors, which haven't been doing any heavy lifting, continue firing at their normal resting rate. The brain calculates movement by comparing the ratio of these signals. Because the down signal has plummeted due to fatigue, the normal resting signal of the up detectors suddenly feels overwhelmingly loud by comparison. The balance is broken. Your brain interprets this imbalance as upward motion. The rocks drift skyward, not because they have moved, but because the neural instruments responsible for seeing them fall have temporarily stopped working. This effect becomes even more surreal when applied to rotation.
If you stare at the center of a spiral spinning inward, your inward motion detectors become desensitized. When you look away at the palm of your hand or a textured wall, the world will appear to balloon outward, expanding and breathing in a distortion that feels almost liquid. It is a reminder that our perception of a stable, still world is actually an active, constant expenditure of energy, a delicate tug-of-war between opposing detectors that can be tipped by something as simple as the flow of a river.
That same sensitivity to flow can be hijacked by images that contain no movement at all, creating a phenomenon known as the peripheral drift illusion. While the waterfall effect requires you to watch a moving object to tire out your neurons, the peripheral drift relies on the fact that your brain processes different brightness levels at slightly different speeds. The most famous example of this is the rotating snakes illusion, developed by Japanese psychologist Akiyoshi Kitaoka. In this image, circular coil-like patterns appear to rotate slowly and continuously, despite the fact that the image is perfectly static. The secret to this phantom motion lies in the precise arrangement of 4 specific luminance levels: black, dark gray, white, and light gray. When these shades are arranged in a repeating sequence, they hack the timing of your visual system. Neural signals do not travel instantaneously. They take time to move from the retina to the visual cortex, and that travel time varies depending on the intensity of the stimulus. Generally, high-contrast inputs, such as black and white, are processed faster than low-contrast inputs, such as dark gray and light gray. When you look at the rotating snakes, the signal from the high-contrast black sections reaches your motion detectors a fraction of a millisecond before the signal from the dark gray sections. This is followed by the white and then the light gray. Because the signals arrive in a staggered timeline rather than simultaneously, the motion detectors in your brain interpret this latency as a shift in position. The neural activity essentially drifts from the faster signal to the slower signal. Your brain assumes that if signal A arrived before signal B, the object must be moving from A to B, creating a perception of rotation in the direction of the luminance gradient. However, this processing delay alone would only create a single momentary jump. To sustain the illusion of continuous rotation, the system needs to be constantly reset. This is where the biological reality of your own eye becomes crucial. Even when you feel like you are holding your gaze perfectly still, your eyes are making microscopic, involuntary movements called microsaccades. These tiny jitters occur constantly, shifting your gaze by minute degrees to prevent your retinal receptors from becoming bleached or fatigued. Every time your eye performs a microsaccade, the image of the snakes shifts slightly on your retina, creating a new onset of visual information. This effectively restarts the neural race between the black, gray, and white segments. The faster signals beat the slower signals to the cortex again and again, triggering the motion detectors repeatedly. This is why the snakes appear to spin endlessly. Your own eye movements are acting as the engine for the movement, refreshing the illusion dozens of times per second. This relationship between eye movement and perception explains the final curious feature of the illusion. The snakes stop moving when you look directly at them. When you fixate your central vision on a specific coil, the image is projected onto the fovea, the small, highly detailed center of the retina. The fovea is optimized for high-resolution static detail rather than motion detection, and when you concentrate specifically on one spot, your microsaccades tend to dampen or become more controlled relative to that target. The peripheral areas, however, remain subject to the drift, meaning the snakes you aren't looking at will always seem to be the ones moving the fastest. This mechanics of deception is what makes the cinema possible. While the peripheral drift illusion relies on the instability of your own gaze, the magic of the movies relies on the limitations of your temporal resolution. Technically, when you watch a film, you're looking at a static wall for the entire duration. Nothing on the screen ever actually moves. The actors, the cars, and the landscapes are frozen in place for every fraction of a second that they appear. The illusion of fluidity is created by the phi phenomenon and beta movement, two distinct psychological concepts that are often grouped together in casual conversation. Beta movement is the perception of a specific object moving from point A to point B. If a light flashes on the left,
Then immediately on the right, your brain insists that the light moved across the space rather than interpreting it as two separate lights blinking in sequence. Max Wertheimer, one of the founders of Gestalt psychology, identified the phi phenomenon as something slightly purer and more abstract, the experience of motion itself, independent of the object. It is a sensation of movement without a defined shape, a signal from the brain bridging the gap between two static events. To maintain this delicate illusion, filmmakers must adhere to a specific speed limit of perception. Scientists have determined that for most humans, individual images begin to blur together into continuous motion at approximately 10 to 12 frames per second.
Below this threshold, we see a jerky slideshow or a flipbook. Above it, we begin to see a simulation of reality. The industry standard of 24 frames per second was established not because it perfectly mimics the human eye, but because it was the minimum speed required to sync audio tracks effectively while remaining economical with expensive film stock. In reality, your visual system is capable of detecting much faster changes. You can perceive flicker at rates up to 60 or even 90 times per second under bright lights, which is why old computer monitors with low refresh rates used to feel exhausting to look at. Yet in a darkened theater, your brain is willing to forgive the low frame rate. It smooths over the transition, ignoring the black shutter that closes between every single frame to advance the film strip. For a significant portion of a 2-hour movie, you are actually staring at a completely black screen, but your mind stitches the lighted moments together so seamlessly that the darkness is effectively erased from your conscious awareness. This neurological editing room works tirelessly to ensure you perceive a continuous world. But this ability to edit out interruptions is not limited to watching screens. It happens constantly in your daily life, specifically every time you shift your gaze. However, if you cease that shifting and hold your gaze perfectly still, locking your focus onto a single point without wavering, a different and deeply soothing phenomenon begins to take hold. This is known as Troxler's fading, named after the Swiss physician Ignaz Paul Vital Troxler, who first described the curiosity in 1804. When you fixate on a specific center point of an image, particularly one with soft, blurry edges and low contrast colors, the surrounding details do not remain constant. Instead, if you can suppress the natural urge to move your eyes for just 20 seconds, the colors in your periphery will begin to desaturate. They soften and lose their vibrancy, slowly dissolving into the background until they disappear completely, leaving you staring at a blank field that is not actually blank at all. This vanishing act occurs because your visual system is wired to detect change, not stability. The photoreceptor cells in your retina are incredibly sensitive, but they are also prone to a specific type of biological boredom. When a light stimulus remains exactly the same on the exact same patch of retina for too long, the neurons eventually stop firing in response to it. They essentially decide that the information is static, safe, and no longer newsworthy, so they stop sending the report to the conscious brain. Under normal circumstances, your eyes prevent this fading through tiny involuntary jitters called microsaccades, which shift the image just enough to keep the retinal cells active and refreshed. But when you concentrate on stillness, you dampen those jitters, allowing the world to simply fade away. This process is a specific visual example of a universal principle called neural adaptation, which applies to almost every sense you possess.
It is the reason you are currently not overwhelmed by the sensation of the fabric of your clothing resting against your skin. When you first get dressed, your tactile receptors send a flurry of signals registering the texture, weight, and temperature of the material. But within minutes, those receptors adapt to the constant pressure. Because the signal isn't changing, the brain tunes it out, allowing the sensation to recede into the background noise of your nervous system. You only feel your socks or your shirt again if you move suddenly or specifically direct your attention towards them. Perhaps the most persistent example of this neurological editing is sitting right between your eyes. Your nose is constantly within your peripheral vision, blocking a significant portion of the view for each eye individually, yet you almost never see it. Your brain has adapted to this permanent, unchanging obstruction and simply paints it out of the final image, stitching together the views from the left and right eyes to create a seamless panorama where the nose does not exist. This biological frugality is driven by the need for energy conservation. The brain consumes a disproportionate amount of your body's energy reserves, roughly 20% of your calories for an organ that weighs only a few pounds. Processing every single photon of light, every thread of fabric, and every static object continuously would be a waste of precious fuel. By ignoring the unchanging parts of the world, the brain frees up processing power to detect what actually matters: movement, change, and the unexpected. It is a system designed to highlight the new by gently quieting the old. This filtering process goes beyond merely ignoring the static. It also involves actively resolving conflicts between the two distinct cameras mounted on your face. Under normal circumstances, your left and right eyes act as a cooperative team, providing two slightly different angles of the same scene that the brain fuses into a single, three-dimensional picture. However, we can trick this cooperative system into a chaotic state known as binocular rivalry, revealing just how much editing happens behind the scenes of your perception. Consider the classic hole-in-the-hand illusion, a simple experiment that requires nothing more than a sheet of paper rolled into a tube.
When you hold this tube up to your right eye and look through it, while simultaneously holding your open left hand right next to the far end of the tube, your brain is suddenly presented with two completely incompatible realities. The right eye reports a circular view of the room ahead, framed by the darkness of the cylinder. The left eye, meanwhile, reports the solid, opaque texture of your palm. Logic suggests you should see one or the other, or perhaps a ghostly, transparent overlay. But the brain prefers a coherent narrative over a messy double exposure. It attempts to merge the data in a way that makes sense spatially, even if it is physically impossible. It takes the clear circular opening from the right eye and superimposes it onto the dominant image of the hand from the left. The result is the striking and somewhat unsettling illusion that you have a clean circular tunnel running straight through your flesh. This phenomenon proves that the brain does not simply blend contradictory inputs like mixing paint. If it did, showing a red image to one eye and a green image to the other, you would see yellow. Instead, the brain engages in a struggle for dominance. It refuses to merge distinct patterns that don't belong together. If you were to look at vertical stripes with one eye and horizontal stripes with the other, you would not see a plaid grid. You would witness a dynamic, shifting mosaic where patches of vertical and horizontal lines fight for territory, appearing and disappearing as neurons compete to signal which view is the true reality. This competitive mechanism is usually reserved for handling the subtle disparities that give us depth perception, or stereopsis. Because our eyes are set a few inches apart, the brain constantly calculates the difference between the two inputs to triangulate distance. This biological triangulation is precisely what 3D glasses exploit. By using polarized lenses or color filters to force a slightly different image into each eye, filmmakers trick the brain's depth processing software into constructing a third dimension on a flat screen. In every moment of vision, your brain is acting less like a passive camera and more like a film director in an editing suite. It has access to 2 live feeds, but it must decide instantly which feed contains the most relevant data. When the feeds clash, the director doesn't panic. It makes an executive decision, suppressing the confusing data from one eye to prioritize the clarity of the other. It chooses a stable, if fabricated, view of the world over the chaotic truth of raw sensory input. This preference for a coherent narrative over a strictly accurate one is perhaps nowhere more evident than in the very architecture of the eye itself. Every human retina contains a significant flaw, a permanent interruption in the visual field where the optic nerve creates a tunnel to exit the eye and travel toward the brain. Because this physical conduit requires a cannula for roughly 1 million nerve fibers, there is no room for photoreceptors at this specific junction. It is a total physiological dead zone, a place where light strikes the back of the eye, but absolutely nothing is recorded. By all rights, every human being should see a gaping black hole floating in their peripheral vision at all times, a terrifying void in the visual field roughly the size of a tennis ball held at arm's length. Yet we never see this darkness. We never notice the gap. The brain does not simply ignore the lack of data, it actively conceals it. This process is known as filling in, or perceptual interpolation, and it is far more sophisticated than simply blurring the edges of a picture. When the visual cortex receives no input from that specific patch of the retina, it instantaneously samples the surrounding texture and color. It essentially clones the adjacent pattern and pastes it over the void, acting much like the digital healing tool in modern photo editing software. If a person looks at a brick wall and the blind spot falls on a specific brick, the brain will construct a phantom brick to ensure the wall looks solid. It is a prediction, a calculated guess based on probability, effectively painting over the structural defect of the eye with a hallucinated reality that matches the context. Scientists have probed this mechanism with fascinating results to see just how far the brain is willing to go to maintain this illusion. In controlled experiments, if a bright red line is drawn so that it passes through the blind spot, the subject does not see a broken line. They see a continuous, unbroken stroke. The brain assumes the line continues because that is the most logical explanation for the data on either side of the hole. Neuroscientists have found that during this process, the neurons in the primary visual cortex actually fire as if they were seeing the red line, even though the eye itself is seeing nothing. The illusion is indistinguishable from reality at a neural level. However, this assumption has limits which reveal the trick. If researchers place a complex word or a set of random numbers entirely within the blind spot against a white background, the brain cannot guess the content. Instead of inventing letters, it simply erases the space, filling it with the surrounding whiteness. The subject perceives a blank sheet of paper, completely unaware that a word is staring them in the face, invisible only because the brain decided that a seamless white background was the statistically safer bet. This reveals that a portion of what is seen at any given moment is not a recording of the outside world, but a real-time computer graphic generated to keep the viewer calm and oriented. The illusion of continuity is so vital that the brain applies this same logic beyond the visual spectrum. Just as the eyes have a blind spot that gets painted over, the ears have their own version of filling in. We often assume hearing is a passive recording device, like a high-fidelity microphone. But the auditory cortex is just as prone to editorializing as the visual cortex, leading us away from optical illusions and into the realm of sonic trickery. One of the most striking demonstrations of this is a phenomenon known as the McGurk effect, a glitch in the matrix of our senses that was discovered almost by accident in 1976. Researchers Harry McGurk and John MacDonald were investigating how infants perceive speech, but they stumbled upon a peculiarity in adult perception that fundamentally changed our understanding of how the brain processes language. The setup is deceptively simple, yet the result is baffling every single time you witness it, no matter how prepared you are for the trick. Imagine you are watching a video of a person speaking. Their lips are clearly moving to form the syllable "ga," with that characteristic opening of the mouth and the tongue pulling back. However, the audio playing over the video is actually a recording of someone saying "ba," a sound that requires the lips to press together and release a burst of air. So you have clear visual information saying "ga" and clear auditory information saying "ba." Logic suggests you should simply hear the audio as it is, perhaps noticing that the lip sync is off like a badly dubbed movie. But the human brain does not settle for a sync error. Instead of reporting what your ears actually hear or what your eyes actually see, your brain frantically tries to reconcile the two conflicting streams of data and synthesizes a completely new reality to solve the puzzle. It fuses the inputs together to create a compromise sound, commonly perceiving the syllable "da." You see "ga," you hear "ba," but you perceive "da." This isn't a conscious choice, a guess, or a simple confusion. It is the raw auditory experience your brain delivers to your conscious mind. If you close your eyes, the illusion instantly vanishes and you hear the correct "ba" sound again. Open them, and the "da" returns immediately. This dominance of vision over hearing highlights just how heavily we rely on visual cues to construct our auditory world. It turns out that we are all lip readers, whether we realize it or not. In a crowded, noisy restaurant, you might think you are straining your ears to hear your friend speak, but your brain is actually leaning heavily on the shape of their mouth to distinguish between similar frequencies. When the visual signal is removed, comprehension often drops significantly because the brain loses its anchor. This reliance on expectation and visual context leads to fascinating errors in daily life, where the brain simply overwrites the audio track with what it assumes should be there. I'm curious if you have ever had a moment where you misheard a song lyric or phrase for years simply because your brain expected one word and refused to hear the actual one. It's a common experience to sing along with total confidence, only to realize much later that the artist was saying something entirely different. So feel free to share your best misheard lyric stories in the comments. That tendency to overwrite reality with expectation is the engine behind the McGurk effect. The brain prefers a coherent story over accurate raw data. Because the visual of the lips pressing together for a "ba" sound is missing, the brain rejects the auditory signal as improbable. It searches its internal database for a sound that shares characteristics of both the visual "ga" and the auditory "ba," landing on "da" or "tha" as the most logical mathematical solution to the sensory equation. What makes this illusion so robust is that it's cognitively impenetrable. You can know exactly how it works, you can have the mechanism explained to you in detail, and you can tell yourself it is actually "ba." But as long as your eyes are open, the illusion persists.
It suggests that this processing happens deep in the primary sensory cortices, specifically in the superior temporal sulcus, long before the information reaches the parts of the brain responsible for conscious thought or decision-making. We are effectively hallucinating the sound da because our visual system bullies the auditory system into submission, proving that hearing is not a standalone sense, but a collaborative effort where the eyes often cast the deciding vote. This integration is usually seamless, stitching together the sensory world so tightly that we never notice the seams until an experiment like this pulls at the loose threads. But sometimes these loose threads are woven into a loop that has no beginning and no end, creating a paradox that traps the ears in a cycle of infinite motion. This is the domain of the shepherd tone, often described as an auditory barber pole. Just as the red and white stripes on a barber pole appear to spiral upward forever while never actually leaving their casing, a shepherd tone creates the distinct, undeniable sensation of a sound that is constantly rising in pitch, getting higher and higher, yet never actually moving anywhere.
The illusion, named after the cognitive scientist Roger Shepard, who demonstrated it in 1964, is a masterclass in how the brain prioritizes direction over location. To build this sonic staircase, you cannot simply use a standard musical scale. Instead, the tone is constructed by stacking sine waves on top of each other, separated by octaves. In music theory, notes that are an octave apart share the same pitch class. They sound like the same note, just higher or lower in register. The shepherd tone exploits this similarity by layering these octaves and carefully managing their volume. Imagine 3 layers of sound moving upward together. The middle layer is loud and clear, anchoring your attention. The highest layer is quiet and getting quieter, fading into silence as it reaches the top of the spectrum. Meanwhile, the lowest layer is barely audible, slowly fading in from silence at the very bottom. As the tones slide upward, the top layer disappears entirely, the middle layer becomes the high layer, and the bottom layer rises to take the place of the middle one. Because the notes are identical in pitch class, your brain fuses them into a single cohesive sound. You hear the rising movement clearly, but you fail to notice that the new bass note has sneaked in to replace the one that just moved up. It is a seamless acoustic handover, a relay race where the baton is passed in the dark, tricking the mind into perceiving an endless ascent. This infinite loop is more than just a laboratory curiosity. It is a powerful tool for emotional manipulation. Filmmakers, particularly Christopher Nolan, often utilize the shepherd tone to induce a subconscious state of anxiety. In movies like The Prestige or Dunkirk, the score utilizes this perpetually rising pitch to create a feeling of unresolvable tension. The brain hears the pitch going up and instinctively prepares for a climax, a peak, or a resolution. But because the tone is looping, that resolution never comes. The intensity feels like it is building forever, hacking the nervous system to keep the audience on the edge of their seats, waiting for a drop that the mathematics of the sound wave will never permit. Yet, when stripped of its cinematic urgency, the shepherd tone becomes a rhythmic, almost meditative example of how our minds construct reality. It reveals that we do not hear absolute frequencies as much as we hear relationships between them. Our auditory cortex is a prediction engine, assuming that a sound moving up must continue to go up. It glosses over the subtle fade-ins and fade-outs, smoothing over the cracks to present a coherent, if impossible, reality. It is a reminder that what we perceive as a continuous flow of time and sensation is often a series of discrete inputs that the brain has artfully stitched together to create a story it can understand. This storytelling instinct extends beyond just visual gaps and into the realm of sound, where the brain is equally adept at fabricating clarity out of chaos.
Perhaps the most famous modern example of this auditory reconstruction occurred in May of 2018 when a short, low-quality audio clip divided the internet into two passionate camps, those who heard the name Yanny and those who swore the robotic voice was saying Laurel. This was not a simple case of mishearing, but a profound demonstration of how our physical biology and mental expectations collaborate to create our subjective reality. The secret to this illusion lies in the physics of sound waves and a phenomenon known as frequency priming. When you analyze the audio file using a spectrogram, which is a visual representation of the spectrum of frequencies in a sound, you discover that the clip actually contains the acoustic information for both words simultaneously. The sounds that form the word Yanny are concentrated in the higher frequency bands, specifically above 4,500 Hz, while the acoustic cues for Laurel reside in the lower frequencies. The recording is essentially a hybrid, an ambiguous signal that forces your brain to make a choice based on which frequencies it prioritizes. This prioritization is heavily influenced by the hardware of your ears. As we age, the tiny hair cells in the cochlea that are responsible for detecting high-pitched sounds naturally degrade, a process called presbycusis. Consequently, older listeners or those with some high-frequency hearing loss are physically less capable of hearing the sharp, higher-pitched variants of Yanny, leaving only the lower, smoother rumble of Laurel to be processed. However, biology is half the equation. The device you listened on played a crucial role. Cheap smartphone speakers often lack bass response, artificially amplifying the Yanny frequencies, while high-quality headphones might emphasize the bass, revealing Laurel. But even more fascinating is the psychological concept of priming. Experiments showed that if a listener was shown the word Yanny written on a screen moments before the audio played, their brain would isolate the high-frequency patterns to match the visual expectation. This is top-down processing in action. Your brain is not merely a passive receiver of sound waves, but an active predictor. It anticipates what it is about to hear and tunes its sensitivity to finding that specific pattern within the noise. The ambiguity of the clip was accidental, born from a poor-quality recording of the word Laurel from an online dictionary, re-recorded through speakers, which introduced noise and distortion.
This degradation is what created the illusion. Because the information was incomplete and noisy, the brain had to fill in the gaps, much like the blind spot in your vision. It creates a bistable perception, similar to the visual illusion of the vase and the two faces. You can technically hear the raw noise, but your conscious mind refuses to accept unstructured static. It insists on meaning. It grabs onto the frequency band that is loudest or most familiar and suppresses the other, effectively editing the audio in real time before you're even aware of it. It serves as a humbling reminder that two people can experience the exact same physical stimulus and perceive two completely different yet equally valid realities. This divergence in reality becomes even more pronounced when we explore the strange world of the tritone paradox. Imagine listening to two computer-generated tones played one after the other. The interval between them is exactly half an octave, a tritone. You're asked a simple question: did the pitch go up or did it go down? It seems like an objective test with a clear right answer. However, if you play this sequence to a room full of trained musicians, a gentle chaos ensues. Half the room will be absolutely certain the notes ascended, while the other half will be equally convinced they descended. This isn't a matter of poor hearing or musical training. It is a fundamental difference in how our brains map sound. Diana Deutsch, the psychologist who discovered this illusion, revealed that our brains have a preferred pitch template, almost like an internal compass that decides which notes are high and which are low based on their position in a circular loop of pitch classes.
What makes this truly haunting is the source of that template. Research suggests that the way you hear these tones is likely determined by the dialect or language you grew up speaking. The intonation patterns of your childhood environment, the way your mother raised her voice at the end of a question, or the specific lilt of your hometown accent imprinted a musical map onto your auditory cortex. A listener raised in the south of England might hear the melody fall, while a listener from California hears it rise. It is a striking realization that your geography is not just where you live, but actually shapes the physical way you hear music. You are carrying the soundscape of your childhood home inside your mind, and it is actively filtering the world you encounter today. Our auditory system is not just a passive receiver, it is a desperate seeker of patterns. This drive is best exemplified by the phantom words illusion. In this experiment, you listen to a recording of repeating words or phrases overlapping in stereo, often sounding like rhythmic white noise or gibberish. After a few moments, something eerie happens. Your brain begins to extract specific phrases that aren't actually there. You might hear words related to your current worries, your name, or random sentences in your native language. Even more fascinating is that two people listening to the exact same track will hear different sentences. The audio hasn't changed, but your brain, unable to tolerate chaos, sculpts the noise into speech. It projects meaning onto the static, effectively hallucinating voices to make sense of the sensory input. It shows that we don't just hear with our ears, we hear with our expectations, our memories, and our fears. Yet sound is not the only sense where the brain constructs a convenient fiction. Just as we can hallucinate words in static, we can also hallucinate the location and ownership of our own physical bodies. The boundaries of the self are far more fluid than we believe, leading us away from the auditory cortex and toward the somatosensory system, where the sense of touch can be tricked into claiming objects that do not belong to us. This phenomenon is most famously demonstrated in a study known as the rubber hand illusion, a simple yet profound trick that exposes just how tentative our grip on physical reality actually is. In the standard setup, a participant sits at a table with one arm resting comfortably but hidden behind a vertical screen. In front of them, in full view where their hand would naturally be, lies a lifelike rubber hand. At first glance, the object is clearly a prop, a piece of plastic distinct from the biological body. The participant knows their real hand is just a few inches away behind the barrier, safe and unseen, but the brain's loyalty to reality is easily swayed by synchronized stimulation. The researcher begins to stroke the participant's hidden real hand and the visible rubber hand simultaneously with two identical paintbrushes. The strokes are applied at the exact same rhythm, in the exact same direction, and with the exact same pressure. For the first few moments, the mind separates the two events. You feel the brush on your hidden skin, and you see the brush on the plastic fingers. However, the human brain is fundamentally a correlation machine, desperate to make sense of incoming data. It sees the touch and feels the touch happening in perfect unison. Within less than a minute, often as quickly as 15 seconds, a strange sensory merger occurs. The sensation of touch migrates. The participant stops feeling the brush behind the screen and begins to feel it effectively inside the rubber hand. The plastic limb suddenly feels warm, alive, and undeniably part of the self.
This reveals a stunning flexibility in what neuroscientists call the body schema. We often assume our internal map of the body is a fixed, unchangeable architectural blueprint established at birth and cemented by years of living in our own skin. In reality, the body schema is more like soft clay, constantly being reshaped and updated based on current sensory inputs. This rapid neuroplasticity occurs because vision is our dominant sense,
often overriding proprioception, which is the internal sense of where our limbs are positioned in space. The brain decides it is more plausible that the hand it can see is the one doing the feeling, rather than the invisible hand hidden behind a wall. The illusion is so complete that it engages the body's deepest defense mechanisms. If the researcher were to suddenly slam a hammer down onto the rubber hand, the participant's real body would recoil in genuine fear. Their heart rate would spike and their skin conductance would change, signaling a fight or flight response to protect a piece of inanimate rubber. We feel a phantom threat to a limb that has no nerves simply because the brain has temporarily adopted it. This implies that the feeling of ownership over our bodies is not a fundamental, unshakable fact of existence, but a continuous, active construction. We are not born with a rigid boundary of where we end and the world begins. We negotiate it moment by moment. If a rubber hand can be integrated into the self so easily, it opens the door to understanding how we might eventually incorporate tools, advanced prosthetics, or even digital avatars as seamless extensions of our biological form, further blurring the line between man and machine. This blurring of boundaries becomes even more profound when we consider the haunting phenomenon known as phantom limb syndrome, where the map of the body persists long after the territory itself is gone. For decades, medical science treated the sensation of a missing arm or leg as a psychological delusion, a form of wishful thinking by a grieving mind, yet the experience is undeniably physical for those who endure it. A person might feel their missing fingers clenching so tightly that their Niffendales seem to dig into a palm that is no longer there, creating excruciating pain that traditional painkillers cannot touch because the source of the pain is not in the stump, but deep within the architecture of the brain itself. To understand why this happens, we must look at the cortical homunculus, the brain's internal map of the body, which is draped across the surface of the brain like a headset. On this sensory map, the area corresponding to the hand is not located near the arm, but is instead inexplicably situated right next to the area that maps the face. This geographic proximity on the brain's surface leads to remarkable cross-wiring. When the sensory input from a hand is suddenly silenced due to amputation, the neurons in the brain do not simply go dormant. Instead, they hunger for input, and the sensory fibers from the neighboring face region begin to invade the silent territory of the missing hand. The result is that if you touch the cheek of a patient with a phantom arm, they may vividly feel that touch on their missing thumb or pinky finger, a precise perceptual illusion that proves the adult brain is capable of massive reorganization. However, this reorganization often results in learned paralysis, where the brain sends a command to the missing arm to move, receives no visual confirmation that the arm has obeyed, and eventually locks the phantom limb into a frozen, painful cramp. The neuroscientist V.S. Ramachandran hypothesized that if the primary issue was a lack of visual feedback, he could essentially hack the brain's reality using a simple optical trick. He developed the mirror box, a cardboard box with a vertical mirror in the center. The participant places their intact arm on one side and the stump on the other, then looks into the mirror at the reflection of their good hand, which is positioned exactly where the phantom limb feels like it should be. When the participant moves their intact hand while looking at the reflection, the brain receives a flood of visual data reporting that the phantom limb has been resurrected and is moving painlessly. This visual input is so powerful that it overrides the sensory silence. The brain accepts the reflection as truth. Patients who had suffered for years with a phantom fist clenched in agony found that upon seeing the reflection uncurl, they felt their phantom fist uncurl as well, instantly releasing the phantom pain. It's a striking demonstration that pain is often a construct of the brain's opinion on the body's state, and by feeding the mind a therapeutic illusion, we can trick the brain into healing itself. This malleability of self-perception extends beyond the management of pain and into the very geometry of the body itself. In the late 1980s, researchers discovered a bizarre phenomenon that famously became known as the Pinocchio illusion. In this setup, a participant sits quietly, blindfolded, and is asked to touch the tip of their nose with their finger. It seems like a simple, fundamental motor task, one that requires no thought. But while the subject holds this position, the researcher applies a specialized mechanical vibrator to the tendon of the biceps muscle, the muscle responsible for flexing the arm.
This device vibrates at a high frequency, roughly 100 Hz, which creates a specific and powerful sensory trick. To the sensory receptors buried deep within the arm, this vibration is indistinguishable from the signals sent when a muscle is stretching. Consequently, the brain receives a flood of urgent data indicating that the biceps are lengthening and the arm is extending away from the face. However, the tactile sensation of the fingertip touching the nose remains constant. The brain is suddenly faced with a physiological contradiction. It possesses two conflicting truths. The arm is moving away, yet the finger is still touching the nose. To resolve this impossible conflict, the brain constructs a new reality that fits the available data. It concludes that the nose itself must be growing longer, extending outward to keep in contact with the retreating hand. Participants frequently report the distinct, undeniable sensation that their nose has stretched outward by several inches, a literal manifestation of the puppet Pinocchio. This distortion reveals the existence of a quiet, often overlooked sensory system known as proprioception. While we are taught from childhood about sight, sound, smell, taste, and touch, proprioception is the body's true sixth sense, the silent, continuous awareness of where our limbs are located in space. It is the reason you can touch your nose in complete darkness or walk without watching your feet. These internal navigation systems rely on microscopic sensors embedded within the belly of skeletal muscles called muscle spindles. These spindles act as biological strain gauges. They are wrapped around muscle fibers like small coils. When a muscle stretches, the coil opens, firing signals to the central nervous system to report the change in length and position. The vibration used in the Pinocchio illusion effectively hacks this communication line. It overstimulates the muscle spindles, causing them to fire rapidly, mimicking the neural pattern of extreme stretching. Because the brain trusts this internal data implicitly, it rewrites the body schema, the mental map of your physical form, in real time. It proves that our sense of physical self is not a fixed, rigid object like a statue, but a fluid, dynamic calculation that is constantly being updated. We are, in a neurological sense, improvised. If the brain can be so easily deceived about the boundaries of its own body, mistakenly believing a nose is a foot long, it raises profound questions about how accurately we perceive the world outside of our skin. Just as we construct our internal posture, we must also construct the stability of the environment around us. This reliance on internal construction suggests that our visual experience is not a faithful, continuous recording of reality, but rather a series of rapid snapshots stitched together by the brain. We operate under the confident assumption that if a significant object were to change color or disappear right in front of our eyes, the difference would be jarring and impossible to miss. Yet scientific literature is filled with evidence to the contrary, demonstrating a phenomenon known as change blindness. This cognitive gap reveals that unless we are paying close, active attention to a specific detail, we are effectively blind to it, even if it changes dramatically. One of the most famous and theatrical demonstrations of this limitation was conducted by researchers Daniel Simons and Daniel Levin in 1998 in a classic experiment often referred to as the door study.
The setting was a busy college campus where an investigator stopped a random pedestrian to ask for directions. As the pedestrian began to explain the route, the interaction was deliberately interrupted. Two people dressed as workmen, carrying a large wooden door, walked directly between the investigator and the pedestrian, momentarily blocking their view of one another. During that split second when the door obscured the scene, the original investigator grabbed the back of the door and walked away with it, while the second investigator, who had been concealing himself behind the door, stepped off and took his place. The new person was wearing different clothes, had a different physical build, and spoke with a different voice. Despite these obvious physical differences, approximately 50% of the pedestrians simply continued giving directions to the new person, completely failing to notice that they were now talking to a stranger. This result seems baffling because it violates our intuitive sense of awareness, but it highlights how the brain prioritizes information. When we look at a scene, we do not encode every pixel of feature. Instead, we extract the gist. The pedestrian's brain had categorized the interaction as giving directions to a student, tagging the person merely as the asker. Because the social category remained the same, the brain did not feel the need to re-verify the specific visual details, effectively overwriting the image of the first man with the presence of the second. This efficiency comes at a cost, creating blind spots that affect us daily, often leading to moments of confusion that we quickly dismiss. It is highly likely you have experienced a domestic version of this phenomenon. Have you ever found yourself frantically searching for an item, like your keys or your glasses, scanning a room repeatedly, only to realize moments later that the object was sitting right on the table in front of you, or perhaps even being held in your hand?
If you have a specific memory of looking right at something but failing to see it until your attention shifted, let me know in the comments, as that experience is the essence of this perceptual gap. Psychologists refer to our feeling of seeing everything at once as the grand illusion of perception. We believe we see the world in rich, high-resolution detail from edge to edge, but in reality, our visual attention is like a narrow spotlight. We only truly see what falls within that beam, while the brain fills in the periphery with assumptions and memories. This occurs because visual working memory is incredibly limited. We can only hold a tiny amount of visual information active at any one moment. When the door interrupted the view, the visual information of the first experimenter was discarded to make room for new input. Since the brain decided the specific identity of the stranger wasn't critical for the task of navigation, it didn't bother to compare the pre-door image with the post-door reality. We navigate the world with a sense of continuity that is largely a mental fabrication, relying on the stability of the environment to store details for us, rather than keeping them in our heads. This creates a profound vulnerability in how we perceive the world, revealing that looking is not the same as seeing. This specific gap in our awareness was famously demonstrated in 1999 by psychologists Christopher Chabris and Daniel Simons at Harvard University, who devised what is now known as the invisible gorilla experiment. The setup was deceptively simple, designed to test the limits of visual attention by occupying the brain with a demanding task. Participants were asked to watch a short video of two teams playing basketball, one team wearing white shirts and the other wearing black shirts. The task was to silently count the number of passes made by the team in white, a chore that requires a surprising amount of cognitive focus because the players are constantly moving, weaving in and out of the frame. While the observer is busy counting aerial passes and bounce passes, meticulously tracking the white shirts and ignoring the black ones, something absurd happens on the screen. A person wearing a full-body gorilla suit strolls into the middle of the circle of players. The gorilla stops in the center of the frame, turns to face the camera, thumps its chest, and then casually walks off screen.
The gorilla is visible for 9 seconds, occupying a large portion of the visual field. When the video ends, the researchers ask the participants to report the number of passes, but then they ask the critical question, did you notice anything unusual? Remarkably, in the original study, 50% of the participants missed the gorilla entirely. They had been looking directly at the screen. Their eyes had almost certainly scanned over the area where the gorilla stood, yet their brains had completely erased it from their conscious experience. When these participants were shown the video a second time without the burden of counting passes, they were often shocked, sometimes even accusing the researchers of switching the tape, unable to believe they could miss something so obvious. This phenomenon is called inattentional blindness, and it illustrates a fundamental truth about the human mind. We do not see the world like a video camera passively recording everything in front of us. Instead, our attention acts more like a spotlight than a floodlight. A floodlight illuminates everything in a wide area with equal intensity, but a spotlight illuminates only a small specific circle, leaving everything else in the shadows. When we focus intensely on a specific task, such as counting passes or tracking a white shirt, our brain actively inhibits information that it deems irrelevant. The gorilla, because it was black, was filtered out along with the black-shirted players. The brain decided that to succeed at the assigned task, it needed to ignore dark moving objects, so it suppressed the visual input of the gorilla before it ever reached conscious awareness. This mechanism has serious implications far beyond the psychology laboratory, particularly when it comes to safety and driving. This is often the cause of the looked but failed to see accidents that occur on our roads. A driver approaching an intersection may look left and right, scanning specifically for other cars and trucks, large, fast-moving objects that pose a threat. Because their spotlight is tuned to detect cars, they may look directly at a motorcycle or a bicycle but fail to register its presence. The cyclist is the invisible gorilla. The eyes capture the image, but the brain does not process it because it does not match the template of what the driver is actively seeking. We assume that if something is important or dangerous, it will automatically grab our attention, but the science suggests that unless we are looking for it, even a gorilla thumping its chest can remain invisible. Just as our eyes can fail to see a large object right in front of us because our attention is elsewhere, our internal sense of time is equally susceptible to manipulation. We tend to view time as a continuous river, a constant metronome ticking away in the background of our lives. But physiologically, time is a constructed narrative stitched together by the brain from fragmented moments. Nowhere is this more apparent than in the phenomenon known as the stopped clock illusion.
You may have experienced this strange sensation when glancing up quickly at an analog clock on the wall. For a brief, confusing moment, it often seems as though the second hand has frozen in place. It hangs there, lingering far longer than a single second should, defying the steady rhythm you expect. You might momentarily think the battery has died or the mechanism is jammed, but then, with a familiar tick, the hand moves again, resuming its normal pace. This is not a mechanical failure, nor is it a simple error in judgment. It is a sophisticated editing trick performed by your visual cortex. To understand why time seems to stretch, we must first look at how our eyes move. Unlike a smooth panning cinema camera, our eyes do not glide across a scene. Instead, they dart rapidly from one focal point to another in quick, jerky movements known as saccades. If your brain processed visual input during these high-speed movements, your vision would be a constant nauseating blur of motion streaks, rendering the world unintelligible. To prevent this disorientation, the brain engages in a clever bit of neurological editing called saccadic masking. Whenever your eyes launch into a saccade to look at a new object, your visual system effectively cuts the feed. For that split second of movement, your vision is suppressed.
You are, for all intents and purposes, partially blind during these transitions. Since we move our eyes tens of thousands of times a day, we spend a significant portion of our waking lives in this visual blackout, yet we never perceive the darkness or the interruption because the brain hides the gap. It waits for your eyes to land on their new target, in this case, the face of the clock. Once the eyes stabilize and the image of the second hand is clear, the brain performs a feat that resembles a minor form of time travel. It takes that clear image of the stationary clock face and backdates it. The brain pastes the clear image backward in time to fill the empty gap left by the eye movement. Essentially, your brain tells you that you were looking at the clock during the time you were actually moving your eyes. Because of this temporal edit, you perceive the second hand as being stationary for the duration of the eye movement plus the actual duration of the second. The first second you see feels significantly longer than every second that follows because your brain has manufactured a memory of it to cover its tracks, smoothing over the seams of reality so you can relax into a seamless experience of the world. This manipulation of the clock isn't limited to a single frozen moment, but actually extends into how you perceive the relationship between time and space, a phenomenon researchers call the kappa effect. If you were to sit in a dark room and watch a sequence of 3 lights flash at different positions, your brain would begin to perform a strange calculation that mixes geometry with duration. Imagine 2 intervals of time between these flashes that are chronologically identical, exactly 1 second apart. However, if the physical distance between the second and third light is much larger than the distance between the first and second, you will swear that the time took longer to pass. Because the light traveled further across your field of vision, your brain assumes it must have taken more time to get there, applying a logic of constant velocity to a situation where nothing is actually moving. It creates a subjective dilation of time simply to make sense of the spatial gap, proving that in the theater of your mind, space and time are inextricably linked, just as they are in the physics of the universe. This elasticity becomes even more apparent when we introduce the element of surprise, often demonstrated through something known as the oddball effect. In this experiment, you might be shown a repetitive series of simple images, perhaps a brown dog, then another brown dog, then another, all displayed for exactly the same number of milliseconds. Suddenly, a bright red flower appears in the sequence for the same duration, yet you will perceive the flower to stay on the screen for significantly longer than the dogs. The novelty of the stimulus jolts the brain into a higher state of alertness, causing it to record the event with greater density and detail. Because you are processing more information per second, the second itself feels expanded, a sensation that offers a profound explanation for one of the most common human complaints about aging. We often wonder why the summers of our childhood felt like endless lifetimes, while a full year of adulthood seems to vanish in a blink. This is largely a result of the same neurological mechanism driving the oddball effect. When you are young, the world is a constant stream of new data. Every experience, from the taste of a new food to the sensation of swimming in the ocean, is a novel event that requires the brain to lay down rich, dense memories. Your internal clock slows down to accommodate this influx of learning. As you age, however, your environment becomes familiar and your daily routines become predictable, allowing your brain to stop recording every detail and simply recognize patterns it has seen 1,000 times before. Without those markers of novelty to anchor your perception, the brain compresses the empty stretches of routine, deleting the commute to work or the weekly grocery run from your conscious timeline, causing weeks to merge into months.
It suggests that the secret to lengthening your life, or at least the perception of it, is to constantly seek out the unfamiliar, forcing your mind to pay attention again. But time is not the only fundamental constant that your mind is willing to distort for the sake of efficiency or narrative. It is quite capable of altering the physical shape of your own body in your awareness. This flexibility extends beyond the sensation of your own limbs and outward into the geometric world before your eyes, where the brain's insistence on creating a stable narrative can be caught in the act of guessing.
One of the most enduring examples of this is the Necker cube, a simple wireframe drawing of a cube first published by Swiss crystallographer Louis Necker in 1832. When you look at this collection of 12 black lines on a white page, there are no visual cues to indicate depth. No shading, no perspective convergence, and no overlapping lines to tell you which face of the cube is in front. Yet your brain refuses to see it as a flat, two-dimensional pattern of polygons, which is what it actually is. Instead, it instantly constructs a three-dimensional box, arbitrarily deciding that the lower left square is the front face. If you continue to stare, however, a sudden and strange reversal occurs. The cube flips, and now the upper right square appears to be the front face, changing the object's orientation entirely. This phenomenon is known as multi-stable perception, specifically bistability, where the sensory input remains exactly the same, but the conscious perception oscillates between two equally valid interpretations. The brain is incapable of holding both versions of reality simultaneously because the visual cortex operates on a principle of mutual exclusivity for object recognition. Just as a physical object cannot be in two places at once, your mind decides that a perceptual object cannot face two directions at once. This battle for dominance is also famously illustrated by Rubens' vase, developed by the Danish psychologist Edgar Rubin around 1915. In this image, you either see a white vase on a black background or two black faces looking at each other on a white background. Your visual system must make an instant decision about figure-ground organization, determining which element is the object of attention and which is merely the background. When neurons representing the face interpretation fire, they actively inhibit the neurons that represent the vase interpretation, a neural competition that ensures you only see one coherent reality at a time. This rivalry becomes even more complex when motion is introduced, as seen in the famous spinning dancer illusion created by web designer Nobuyuki Kayahara in 2003. The image shows the black silhouette of a female dancer pirouetting, and for most viewers, she initially appears to be spinning clockwise. However, for a minority of people, or if you watch long enough, she will abruptly switch and begin spinning counterclockwise. Like the Necker cube, the dancer is an orthographic projection, meaning she has no depth. The image does not change size as it moves away from the viewer, depriving the brain of the standard clues it uses to judge distance. Because the image is a flat silhouette, there is no visual data to confirm whether her left leg or her right leg is passing in front of her body. Confronted with this ambiguity, the brain fills in the missing depth information based on assumptions. Research suggests that the majority of people see clockwise rotation because of a view from above bias. In our daily lives, we more frequently look down at objects than up at them, and assuming a downward viewing angle on the silhouette makes the geometry resolve into a clockwise spin. Ultimately, these illusions reveal that perception is not a passive recording of the outside world, but an active, continuous decision-making process where the brain constantly proposes the most likely hypothesis for what is out there. This hypothesis testing becomes startlingly specific when we look at how the brain handles human faces, revealing that we process other people quite differently than we process objects like chairs or houses. There is a famous demonstration known as the Thatcher effect, named after the former British Prime Minister whose photograph was used in the original 1980 experiment by Professor Peter Thomson. To understand this quirk of cognition, imagine a standard photograph of a face that has been turned upside down. However, there is a clever, subtle alteration hidden within the image. The eyes and the mouth have been cut out, flipped, and pasted back in so they're right side up relative to the viewer, even though the head remains inverted. When you look at this upside-down face, everything seems perfectly fine to your brain, perhaps just a little distinctive, but generally acceptable. Your visual cortex scans the image and reports that the eyes look like standard eyes and the mouth looks like a standard mouth. However, if you were to take that same image and slowly rotate it 180 degrees until it is right side up, the result is suddenly and shockingly grotesque. The features that looked pleasant and normal a moment ago now appear monstrously distorted, with the eyes looking downwards and the upper lip curving bizarrely upward in a way that seems physically impossible.
This jarring reveal occurs because of a dual processing system within human vision. Under normal circumstances, when we see a face upright, we engage in what psychologists call holistic or configural processing. We do not merely see a collection of separate biological parts. We see the precise spatial relationships between the nose, the eyes, the chin, and the mouth all at once, creating a unified map of identity. This is a specialized, high-speed mode of perception that allows us to instantly recognize a friend in a crowd or detect a micro-expression of sadness before a word is spoken. But this biological software is incredibly rigid. It essentially only works when the face is oriented correctly. As soon as a face is rotated upside down, that specialized holistic scanner fails to engage. The brain, unable to use its preferred face reading tool, defaults to a more generic mode called feature-based processing. In this mode, we analyze the face the same way we might analyze a building, a cloud, or a lamp, part by individual part. We check the inventory list. 2 eyes, check. 1 mouth, check. Since the eyes and mouth in the altered photo are technically right side up relative to our point of view, the feature-based system gives the all-clear signal. It lacks the sophistication to understand that the global relationship between the features is completely wrong. It is only when the image flips back to the upright position that our specialized face-detecting machinery located deep in the fusiform gyrus of the temporal lobe kicks back into gear. It instantly assesses the geometry, screams that the configuration is anatomically impossible, and delivers that feeling of visceral wrongness. This illusion serves as a humble reminder that our seamless experience of reality is actually stitched together by different neural subroutines, each with its own specific operating manual, and even our expertise in recognizing one another can be deactivated simply by changing our angle of view. While the inversion effect demonstrates how the brain struggles to interpret unusual angles, an even more profound revelation occurs when the brain is given no angles at all. In the absence of visual input, the mind does not always settle for darkness. Sometimes it chooses to light up the theater on its own terms. This phenomenon is known as Charles Bonnet syndrome, named after the Swiss naturalist who first described it in 1760. Bonnet noticed that his grandfather, who was mentally sharp but nearly blind from cataracts, began to describe vivid, detailed visions that simply were not there. He saw tapestries covered with birds, scaffolding that changed shape, and figures of men and women who would approach him but never speak. What makes this condition so distinct and so scientifically important is that the people experiencing it are entirely psychologically healthy. They are not suffering from dementia or psychosis. They are usually fully aware that the giant flowers blooming on the ceiling or the tiny people marching across the coffee table are hallucinations. This clarity distinguishes Charles Bonnet syndrome as a hallucination of the sane. It strikes those with significant vision loss, such as macular degeneration or diabetic retinopathy, serving as a phantom signal from a system that has been cut off from the outside world. The neurological mechanism behind this is called deafferentation, or sometimes the release phenomenon. Under normal circumstances, the constant flood of information coming in through your eyes keeps the neurons in your visual cortex busy and grounded in reality. But when that input stream slows to a trickle or stops completely, the visual cortex becomes hyper-excitable. It creates a state of sensory deprivation that the brain finds intolerable. To compensate for the silence, the neurons begin to fire spontaneously. The brain, ever the dutiful interpreter, takes these random sparks of electrical activity and tries to make sense of them,
weaving them into the closest recognizable shapes it can find in your memory. It creates a sort of screensaver for the mind. Simple geometric patterns like grids, honeycombs, or tessellated brickwork are common because they correspond to the physical structure of the neuronal columns in the primary visual cortex. As the signals move deeper into the brain's processing centers, the images become more complex, manifesting as disembodied faces with exaggerated eyes, elaborate costumes from previous centuries, or imaginary animals. It is a striking parallel to phantom limb syndrome. Just as a brain might continue to feel a hand that is no longer there, the visual cortex continues to see a world that is no longer visible. Understanding this provides immense relief to those who experience it, many of whom suffer in silence for fear of being labeled mentally unstable. It is a humble reminder that our perception is an active construction, not a passive recording. But if the brain can generate images without eyes, it can also tangle the wires between the senses that remain, leading to a reality where sounds have colors and words have tastes. This distinct neurological trait is known as synesthesia, a term derived from ancient Greek meaning joined perception. For a synesthete, the stimulation of one sensory pathway leads to automatic, involuntary experiences in a second sensory pathway. It is not a hallucination in the frightening sense, nor is it a literary metaphor.
When a synesthete says that the name Alice tastes like apricots, or that a trumpet sounds like purple triangles, they are describing a consistent, repeatable physiological reality. The most common variation is known as grapheme color synesthesia. In this perceptual arrangement, individual letters of the alphabet or numbers are inherently shaded with a specific color. The number 5 might be a vibrant emerald green, while the letter S is a moody, distinct indigo. These associations are incredibly stable over time. If you ask a synesthete the color of the letter M and then ask them again 10 years later without warning, they will likely give you the exact same answer, often distinguishing between very subtle shades that non-synesthetes would miss. Neuroimaging studies suggest that this specific crossover occurs because the brain regions responsible for processing colors and shapes are located right next to each other in the fusiform gyrus. In the brains of synesthetes, there appears to be excess cross-wiring between these neighbors, allowing activity in the letter recognition area to spill over directly into the color processing center. While colored numbers are fascinating, other forms of this condition blur the boundaries of the self even further. Mirror touch synesthesia is a rare and profound variation where an individual literally feels the sensations they witness in others. If a person with this condition sees someone else being tapped on the shoulder, they feel a phantom tap on their own shoulder at the exact same moment. It is believed to be caused by hyperactive mirror neurons, the cells that allow us to learn by imitation and feel empathy. For the mirror touch synesthete, the barrier between their own body and the bodies of others is permeable, turning empathy into a physical, tactile sensation. One of the most compelling theories in neuroscience regarding this phenomenon is the idea that we may all begin our lives as synesthetes. The infant brain is a dense thicket of neural connections with far more pathways linking different regions than an adult brain possesses. This state creates a highly interconnected sensory experience where sounds, sights, and feelings are not yet fully segregated. As we mature, a process called synaptic pruning occurs. The brain efficiently snips away the connections that aren't being used, separating vision from hearing and taste from touch to create distinct specialized senses. The current hypothesis suggests that in adult synesthetes, this pruning process was simply less aggressive, leaving behind ancient bridges between the senses that the rest of us lost in childhood. It makes one wonder about the hidden colors in your own mind. I'm curious if you have a touch of this wiring yourself. Do you have a specific color that you always associate with the number 7, or perhaps a distinct shade for Tuesday? And if so, what are they?
Even if you do not experience the world through the kaleidoscopic lens of synesthesia, your brain is engaged in a constant silent act of creativity that is just as profound. Consider for a moment the physical reality of your own mind. Your brain is locked inside a sealed chamber of bone, encased in total darkness and absolute silence. It has never seen a sunset, it has never felt the texture of velvet, and it has never heard a violin directly. It sits in the dark, receiving only trains of electrical spikes from your sensory organs. From this limited, noisy, and ambiguous data, it must conjure the rich, colorful 3D world you believe you are navigating right now. This isolation leads us to one of the most transformative theories in modern neuroscience, known as predictive coding. For decades, scientists believed the brain operated like a biological camera, passively receiving information from the eyes and ears to build a picture of the world from scratch, pixel by pixel. But as we looked closer at the anatomy of the brain, the math simply did not add up. The signals traveling from our eyes to our visual cortex are surprisingly slow and low resolution. If we waited for our eyes to fully process everything before we reacted, we would be perpetually lagging behind reality, unable to catch a ball or avoid a stumbling block. To solve this latency problem, the brain operates not as a passive receiver, but as a relentless prediction machine. It does not ask what is out there nearly as often as it asks, is the world still doing what I expect it to do? This creates a dynamic interplay between two streams of traffic in your neural pathways. First, there is the bottom-up information, the raw sensory data flowing in from your retina or your fingertips. But rushing to meet it is a massive surge of top-down information, which is essentially your brain's memory and expectations projecting outward. Anatomical studies of the visual cortex have revealed a startling fact. There are significantly more neural connections carrying signals down from the brain's memory centers to the visual system than there are carrying signals up from the eyes. This implies that what we see is primarily a projection of what we expect to see, with just enough sensory input to keep the hallucination anchored to reality. You are not so much seeing the chair in the corner of the room as you are hallucinating a chair based on past experience and then using a tiny fraction of sensory data to confirm it is actually there.
This is why you can read a sentence where the middle letters of every word are scrambled, as long as the first and last letters are in the right place. Your brain isn't reading every letter, it is predicting the words and skimming the bottom-up data just enough to verify the guess. When the internal hallucination matches the external data, we call it perception. When there is a mismatch, say you think you see a coiled snake in the garden, but it turns out to be a garden hose, that is what neuroscientists call a prediction error. The brain hates prediction errors. It immediately scrambles to update its internal model, changing the hallucination to match the new data. This is precisely what happens during visual illusions. When you look at an image designed to trick you, your brain is applying a rule that usually works in the real world, like assuming light always comes from above, or that parallel lines converge in the distance. The illusion persists because your brain prioritizes its internal model, its best guess, over the confusing raw data it is receiving. You might wonder why nature would design a system that is so prone to being tricked. The answer lies in the harsh economics of survival. Processing every photon of light and every vibration of air from scratch is computationally expensive and dangerously slow. A creature that pauses to perfectly analyze a rustle in the grass to determine if it is 100% definitely a tiger will be eaten by the time it finishes the calculation. A creature that predicts tiger and runs immediately lives to pass on its genes. In this light, perceptual illusions are not bugs in the system, they are features. They are evidence of a brain optimized for speed and efficiency rather than photographic accuracy. The brain cuts corners to keep you alive. It fills in the blind spot where your optic nerve exits the eye, not with real data, but with a copy-paste pattern of the surrounding textures. It assumes shadows are gray and not black.
It smooths over the jittery motion of your eyes to create a stable movie of reality. We survive because we are excellent guessers, navigating a world constructed as much by our memories as by the light entering our eyes. This realization changes the way we interpret every glitch and curiosity we have encountered. We started by examining the biological hardware of the eye itself, discovering that what feels like a seamless high-definition video feed is actually a patchy, reconstructed stream of data that the brain stitches together in real time. We saw how the mind quietly edits out the blind spot where the optic nerve leaves the retina, filling the void with whatever texture surrounds it so you never notice the gap. We traced the path of electricity deeper into the visual cortex, where color was revealed to be a relative calculation rather than an absolute truth, shifting and changing just to help us identify a ripe fruit in the shade or a stone under the midday sun. We even explored how the sensation of time itself can warp, slowing down during moments of awe or speeding up when our attention is divided, proving that the mechanical clock on the wall and the internal clock in the mind rarely tick in perfect unison. This accumulation of evidence suggests that we do not live directly in the physical world, but rather in a sophisticated simulation of the world created by our neurons. The brain is effectively locked in a silent, dark vault of bone, receiving nothing but coded electrical spikes. Yet from that limited input, it manages to conjure a universe full of light, depth, texture, and movement. Every illusion we discussed is a testament to the immense creativity of the brain. It prioritizes a coherent story over raw, pixel-perfect accuracy. It filters out the jitter of your eyes to give you a steady horizon and ignores the constant shadow of blood vessels across your retina to give you a clear view. These are not failures of the system, they are the elegant shortcuts that allow consciousness to navigate a complex environment. There is a comforting solitude in this perspective. It means that the reality you experience right now is a custom-made creation, a personal narrative written by your biology. As you rest, the stability of the room and the continuity of your existence are being actively maintained by the quiet, steady hum of your nervous system. It is a protective mechanism, smoothing out the rough edges of sensory chaos so you can exist peacefully within the moment. If you have found value in this journey through the hidden corridors of perception and wish to support more calming explorations of the scientific world, please take a quiet moment to subscribe to the channel before you drift off. As the processing centers of the cortex begin to wind down for the night, the line between perception and imagination grows even thinner. The mind prepares to disconnect from the external senses and turn inward, ready to construct the vivid, logic-defying illusions of the dream state. This is the final frontier of perception, where the brain creates entirely new realities without any input from the outside world. It is a gentle reminder that the most powerful projector of images is not the eye, but the mind itself. Let go of the need to verify what is real and what is fabricated, and simply allow the neural static to settle into silence, trusting your brain to watch over the world until the morning returns.